well, this section of this lecture has certainly been kind of funny. This is now the third time I'm doing this section. The first time my memory card ran out of space. The second time I forgot to turn on the camera. But now everything is working. The red light is blinking. I have 5 hours of memory of time on my camera, and this is gonna not take 5 hours, but we're gonna finish for once and for all. All right, so the Hamiltonian is n plus a half, which we can convert to physical unit Hamiltonian by just multiplying by h bar omega. N, we recall, is a dagger A. N operating on the vector v gives us back v, or we could call it n, doesn't matter, just some number. All right, and so that we figured out that A operating on a v will give us back a vector which, when operated with n on it, will give an eigenvalue that's v minus 1. So we will say that this creates somehow the v minus 1 state. A dagger on v will create somehow the v plus 1. Now, there's going to be an additional factor, multiplicative constant, when we actually do these operators. So that's what we're going to figure out now. And we're going to figure it out by basically doing, by imposing that the vectors stay normalized when we do the different operations to them. Okay, so let's start out how we're going to do that. Remember that what the basic idea was, since this makes us go up and this makes us go down, we can start somewhere in the middle, wherever that happens to be, let's call it v. And we can do an annihilation step here. So apply 1a, and that's going to get us v minus 1. Then we can do it again and get another a, and then v minus 2. And we could keep doing this forever, but eventually what's going to happen is we're going to get to a state where the energy is below the value that is the potential energy function. The potential energy function sets the lower limit. You can't have energy less than the minimum of the potential. In quantum mechanics, especially if the potential is bound, then the energy will always be higher than the minimum. That's the 0-point energy, and it's just a property of confinement. But you could have a potential energy function like a Coulomb potential, which is negative infinity if they're attractive, and then there's no lower limit. You can just keep going lower and lower and lower. But if for a parabola like we have in this case, there is a minimum. So we're going to call that minimum, for sort of perhaps obvious reasons, we're going to call it 0. So let's say whatever the minimum one is, we'll call it 0. And then we're going to build up from the ground floor all the subsequent ones. The problem that's going to happen is we're not the problem, but we want to make sure that when we do that building up process, that the vector stays normalized. So the first thing that we're going to do is we're going to presume that we can find or set the ground state, the 0 energy state, to be normalized, so that this is equal to 1. And that when we keep going up, we're going to get a vector that's also normalized. All right, so the way we do this, the way we figure out what do we need to do to A to make sure that this works, is we simply consider a vector, let's call it z, that is made by operating with A on V. All right, and then we consider the ZZ scalar product. Right, and then that's equal to, by following our Dirac rules, we switch the V from a ket to a bra and A to A dagger. So we have V, A dagger A, V. So the first thing that you probably notice here is that this is N, and we'll come back to that now, later. So that's step 1. All right, so what we want to do is simply break this apart like that and operate with A on V. And what that's going to do is it's going to give us V, A dagger, and then V minus 1 times whatever the number is, whatever the constant is that you get when you operate with A. And that's what we're trying to find out what it is. So we're going to call that, to be very vague, CV. So it's some constant that depends on V. All right, now what we're going to do is we're going to use a property of this scalar product here. So notice this is a scalar product. You can think of it as a scalar product of V with A dagger operating on V minus 1, or you can think of a scalar product of V having operated with, on A dagger to the left with V minus 1. Either way, it doesn't make any difference. But we can use the property that when we flip it around and then put a star, it's exactly the same as this. So v minus 1 is flipping it around. Flipping it around means turning a dagger to a, and v, and then put a star here. That is equal to that. Okay, so now we know what a operating on v does. It gives us back v minus 1 plus times another factor of cv, but now since it's inside this thing, we have to star it. Right, so what does that give us? That gives us v minus 1 from the algebra part, and then the number gives us cv star cv. If we presume, of course, that this vector is normalized, this one was normalized, VV is also going to be presumed to be normalized. So we're assuming the vectors are normalized. We don't want them to be unnormalized. Then, of course, what we have here is that this is equal to the modulus of CV squared. Okay? So let's take a look at the left-hand side now. We know what n operating on V does. It's from our presumed solved eigenvalue problem. And so that means V comes out and we have VV. This is equal to 1. And so that tells us that CV squared is equal to V. All right, now this is a modulus squared, so there's no phase information. I could take CV, whatever it is, and multiply it by e to the I theta, and then this would still work. So that is essentially means there's an infinite number of CVs that satisfy this. But we will make the usual convention that we choose the CV values to be real. If that's the case, then we know we can just convert this to like a normal square. And so then that means that CV is equal to the square root of V. Okay, and so that tells us then that A operating on V will give us the square root of V times V again. And this is in your problem set. I said just assume that this is the case, but here we've proved it. So now there's an alternative, not an alternative, there's an analogous or almost identical way to show all of this similar thing for A dagger. So you would start with A dagger up here, put it into the scalar product. It won't be A dagger A, it'll be A dagger, but that's n plus 1, right? We know how to convert that using the commutator. And then you do the same kind of flipping, flopping, and then notice that it's CV, but now instead of equaling V, it'll be equal to V plus 1. All right, so for A dagger, we end up with V plus 1. Notice my mistake. Well, this is not V, of course, this is V minus 1. All right, so we're almost there. We've figured out the correct full forms of the accretion and annihilation operators. We had the idea that we could take to 0 and apply A dagger to it as many times as we wanted. So we had the idea that we could make the state n by starting with the state 0 and operating with A dagger n times on the state 0. But now we know a little bit more about A dagger, right? A dagger is going to give us a square root in front. Every time we go up, it's going to give us a square root of the upper state that we end up on. All right, so for example, if you make the state 2, the first time you go up, you're going to get a square root of 1. Okay, that's just 1. The second going up is the square root of 2. So this is going to equal the square root of 2 times 2. That's no good. We don't want that. All right, so we want to have no square root here. All right, because of course, this would not be normalized. If we took 2 and took the square root as the scalar product of 2 with itself, we'd end up with getting 2, not 1. That'd be very bad. Okay, so one way to think about this is every time we're going up, we're going to pick up a new square root of the state that's above us. So if we go up to n, so it's going to look like, if we do A dagger n times on the vacuum, on the ground state, we're going to have the square root of 1 times the square root of 2 times the square root of 3 up to the square root of n operating on 0. We want to get rid of all of this. Well, look what this is. This is n times n minus 1 times n minus 2, blah, 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 all the way down to 1, right? And so this is just the square root of n factorial. We don't want that. So how do we do it? We divide by the square root of n factorial at the beginning. So what we do instead to make the state n is we take A dagger, absolutely raise it to the nth power, but then we take care of this extra square root problem by dividing by it on the denominator. And that's it. This is how you get all of the eigenstates of the Hamiltonian They have their eigenstates of the n operator, for sure, but they're also eigenstates of the Hamiltonian, right? We know that. So now we want to figure out what are those energy levels. We know the n's, we can just read them off, but what about the energy levels? Okay, so what we do to do that is we figure out the Hamiltonian operating on the 0 state, and we know that every single one above that is just going to be 1n higher, right? So that's equal to n plus a half operating on 0. So you can immediately just read off, well, n operating on 0 is 0, and so that's a half, so then the eigenvalue would be a half for the Hamiltonian. Or if you don't like that, I mean, I think that's fine, but you can also write a dagger a plus a half operating on 0. The a operating on 0, we said that, it's a minimum one. That's equal to 0, and so you're done with that. All right, so the energy of the ground state is equal to 1/2. The script energy of the ground state is equal to 1/2 h bar omega, the usually the expected minimum energy, the so-called 0-point energy. For some reason, when you see a lot of textbooks, especially in chemistry, people usually only discuss the 0-point energy when they're talking about the harmonic oscillator. But if you look at any bound system, there will be a 0-point energy. It comes out of the fact that there's confinement. This particle in the box energy is not 0. The hydrogen atom is negative because you define it with respect to the infinite separation of the proton. But if you compare the negative 13.6 electron volts of a hydrogen atom to the minimum of the potential, which is negative infinity, it's a lot higher than that, or a lot less negative than that. Okay, so we can, of course, then build up all the subsequent levels because we just have n states, and then you compute the same thing, but as you keep going up. And so then we know that the energy levels will be n plus a half, right? And n goes from 0 and so on. And then the script energy levels, which are the real units ones, are n plus a half h bar omega. All right, so that tells us the energy levels and the eigenvalues and the eigenvectors of the Hamiltonian. And I think this is a really beautiful derivation. It was actually originally due to Dirac himself. So Dirac was the first to really put this together. It became a kind of standard textbook issue in the sort of 40s and 50s. And I think it's a really remarkable way to show how powerful just the simple logic of Hilbert space is in solving this problem, once you know how to recast the position momentum operators into these creation and annihilation operators. Similar strategies are useful in other methods, but reason why I really like this is because there's two reasons, maybe two, but maybe two is a bit too small. First, this is for the Hamiltonian, that's 1/2 p squared plus q squared. All right, that's fine. Harmonic oscillators are awesome, but the world is not made out of truly harmonic oscillators. And so what you might have is a potential energy function that's not just 1/2 q squared, So let's say that the potential energy function is completely generic. So we're going to sum over every possible power of q, and then we're going to have some coefficient, which I might call c of k. So now I could make essentially any potential energy function as just an expansion coefficient times q to the appropriate power, and I add those up. Now, of course, if you had the function in advance, you would just take the derivatives of it and do a Taylor series, and that's where you get the ck's from. All right. Or you can just cook up any potential you want, and as long as you know how to do it with these k's. And then once you have the q, you write the q as a matrix. Right? You make it a matrix expressed in the basis of the harmonic oscillators, and then you raise the q to the appropriate power that you need. And so you just make like a rubber stamp of the matrix, and then you compute the product of those. And of course, computer programs can do that for you very easily. So if you say you want the 9th power of the matrix, you just tell MATLAB or Mathematica or whatever, LAPACK, whatever you're using to do your linear algebra, you say I want the whatever's power of the matrix, and then that's going to be the potential energy term that you need. And you add the next one, and you use the appropriate weighting factor, ck, for each of these. You add them together, plus the p squared over 2m, or p squared part, right? And that's going to be the Hamiltonian, no matter what. you can convert it into real units the way we did this if you want to do that. And so what's nice then is when you solve the eigenvalues and eigenvectors of that new Hamiltonian matrix, you will just simply have all the information in terms of the original basis of the harmonic oscillators. We know the wave functions or the eigenfunctions of the harmonic oscillator, which look like this. You know, you have the Gaussian, and then you have all the subsequent excited states of it. Now to get these, you obviously need to do a little bit more than what we've done. I'm gonna leave it alone here. There's 1,000 textbooks that explain how to do this. And if anyone wants a reference, certainly look in the Green Sites book. It has it. And I just find lots of really good online, you know, other people's lecture notes. But it's basically amounts to doing a differential equation, starting with the ground state. When you do that, you find out you have a Gaussian. And then what you can do from that is you still use the same raising operator to generate all the higher states. You might say, how do I do that? I only know how to do a dagger on these Hilbert space vectors. Well, what you do is you go back from the a dagger back to Q and P. Once you go back to Q and P, it's no problem because that's just going to be Q, which is their variable anyway. And then P, well, the P is just a derivative with respect to Q, right? So what's going to happen is you're going to have a whole series of however many times you did P. So if you do P once, it'll be a derivative. Well, derivative of a Gaussian is going to put, you know, it's going to be, the slope is 0 in the middle. So that's going to be a function like this that has a node in the middle. And if you do the derivative of this, well, it's going to have nodes here and here. And that's why you have these two peaks. So every time you go from here to here, you're just making more nodes by taking the derivative of the function that you started with. So again, you're just going to use the raising operator, but written back in the coordinate representation. And then you can generate the full set. Now you could do that to a fixed order. That would be not super elegant. But all you have to do is dust off your 19th century math, and you will find out that the generating function you get is exactly this sort of so-called Hermite polynomials. And that's what you need in order to multiply the Gaussian function by to get these nodes here. All right, so that's a way of making these. And once you have them, you could then plot in coordinate representation the solutions to any other harmonic or any other mechanical oscillator you have, anharmonic, double well, you name it, right? And so that's really powerful. Now, of course, what's going to happen is the more powers you add, the higher that you need to go in your approximation, the more off-diagonal elements there will be in the Q operator, the potential energy operator, because it's going to have Q to like the 10th power, which will have, you know, up, 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 down, 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 up, 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 whatever you can do to make 10. And there'll be a lot of off-diagonal elements. And the more off-diagonal elements you have, the less your new problem is like the original one that you have the basis for. And so the more basis states you'll need to get a good approximation. Right? So that is the challenge of playing death metal with flutes, is that you'll need a lot of flutes to approximate the sound of the death metal band. All right, so the other reason why this is great, so first reason is because you can do an arbitrary potential in principle. The second reason is because what it does is it allows us to think about quantization sort of separately from the physical system. We can say, oh, I have a bunch of states, I'm going to go up and down with them, and then I can develop an algebra for that. It turns out it's very popular to consider even very complicated systems like photosynthetic bacteria proteins with multiple chromophores inside of them in a very similar way. You say, oh, there's a chromophore over here, and there's a chromophore over here. So these are like, you know, kind of two-dimensional chromophores like chlorophylls and stuff like that. Pheophytin is another one. And if they're nearby to each other, then they can be coupled. And so rather than thinking about this thing as an intractable set of a billion electrons and atoms and stuff, you say, oh, I've got a two-level system over here, I have a two-level system over here, and I have a two-level system over here. I couple them together, and now I have a very simple Hamiltonian that might describe the collective electronic excitations in this. And that's going to be very similar to how we manage vibrational spectroscopy as well. So trying to find similarities is my main goal. So finding connections between this area and that area when you might think they're totally different is great, because if you can connect what you're working on, your problem, to another area that's already been solved, you can somehow figure out a way to sort of transform either their thinking to your problem or your problem to their thinking. And maybe they've been working on it for a long time. So maybe there's already a whole bunch of understanding over there that you can just tap into and be like, whoa, okay, well, we were calling it something totally different, but they call it this, and this is what they've learned from it. And we're going to talk about examples where that turns out to be very fortuitous. There's a lot of systems right now in chemistry where people are connecting pieces together. You might connect a light absorbing part that looks like an antenna to a redox active part, something that can do either catalysis or just chemistry. You absorb the light on one part of the molecule and you transfer the energy over to another part, and then it can do some chemistry over there where the chemistry part might not have a convenient absorption, let's say, in the solar spectrum. That's a very popular thing to do. Other areas where you might think of a similar way would be like if you have aggregates. So if you have a bunch of molecules all sort of stuck together because of their, say, like mutual pi interactions. Well, you can get them to all stick together, and all of a sudden now you have lots of coupling between these. So they're going to make very delocalized excited states, and understanding how those excited states work, for example, if I put energy in on one side, how does it come out on the other side, can give you insight into the transport properties, the charge separation properties, and so on. And a lot of those ideas can be understood within the similar kind of framework, believe it or not, as we've done here with a harmonic oscillator. And I will try to keep some of the jargon out, but sometimes it's really useful to have the jargon in, because then you can say, oh, I get it. You added this coupling between these two harmonic oscillators. Well, the physics people call this a Franco exciton. That's the same thing. All right. So my job is to try to show you how when you have two sides of the same coin, it's really the same coin. All right. Yeah. So this is cool. I hope everybody gets to appreciate the beauty of solving this harmonic oscillator problem using no differential equations at all, just some very basic logic about Hilbert space and some very basic properties of vectors and their scalar products.